Dear students, today we will start with one more numerical on trusses. Again, we'll solve by from the question paper VTU. So here, if you see question number 6b, we have a truss member having two elements. For the two bar truss shown in the figure, determine the nodal displacement. Here we need to determine the displacement of each node. Young's modulus is given, which is 200 gigapascal, which is nothing but 200 into 10 raised to 3 Newton per mm square. Cross sectional area is given, which is 6 into 10 raised to 4 meter square. So we need to convert that in millimeter. So for that, what we need to do is here 6 into 10 raised to 4 into meter square. 1 meter is nothing but 1000 millimeter whole square. If you simplify this, you will get 600 millimeter square. So cross sectional area is nothing but 600 millimeter square. Young's modulus is given. So if you see here in this problem, the length of the if suppose this is the first element, if suppose this is the second element, the length of the first element, which is given here, which is nothing but 4 meter. 4 meter is nothing but 4000 millimeter. So the second element, length of the second element, this is our second element, the length of second element, which we can calculate it by using Pythagoras theorem. Here we can determine by using like under root 4 square plus 3 square, we will get 5 meter, which is nothing but 5000 millimeter. The length of this element is 5000 millimeter. And if you see, the node 1 is fixed, node 3 is fixed, and node 2 having only movement in the x direction, and whereas y direction it is fixed. If you see, this is the roller support. Here you can see this is the roller support, and it is fixed in the vertical direction, and it can move in the horizontal direction. And the application of load, which is in the negative x direction, 1000 kilonewton. So it is nothing but 1000 into 10 raised to 3 Newton. So we'll proceed with the solution so that you can understand. If you see here, like the given data which we have already discussed, first step is to do the modeling. In this, this is our first element, we consider it as a first element. We do write like this. This is the second element, and first element is connected between node 1 and 2, and second element is connected between node 2 and 3. Once we defined the nodes and elements, next we need to define the displacement for the each node. As we know that truss member is a two force member, means at each node we have two displacement. Here we have, in the first node we have displacement u1 in the along the x-axis and u2 in the y-axis. Similarly, in the second node we have displacement u3 in the x direction and u4 in the y direction. Similarly, in the third node we have displacement u5 in the x direction, u6 in the y direction. And length of the second element we have calculated earlier. The length of this element is 5000 millimeter, and length of the first element is 4000 millimeter. Once we do these basic modeling, the next step is we need to calculate the nodal data, nodal connectivity data we can call. Here we take the node 1 as a reference for the coordinates. This we represent 0, 0, means the node 1 is at the fixed position, in the sense it is in the reference position, where along x-axis it is 0, along y-axis is 0. So which we have written here, node 1 which is at 0, 0. In x-axis it is 0 and y-axis it is 0. Similarly, if you see the node 2, which is located here, it is at a distance of 4000 mm from the reference, and whereas it don't have any vertical coordinate, only we have horizontal coordinate. We have written second node, which is 4000 comma 0, or we can write 4000 0 here, which we have written on the x-axis it has 4000, y-axis it is 0. Similarly, we need to write for the third node. This is our third node, and it is at a distance of 3000. It is at a distance of 3000 from the y-axis, and it is 0 from the x-axis. So that's what we have written, 0 comma 3000. And these are nothing but x1, x2, x3 and y1, y2, y3. Once you define nodal connectivity data, next we need to define the direction cosines. So direction cosines are nothing but L and M, which defines the orientation of each bar. Here the direction cosines are, for the first element, L is equal to x2 minus x1 divided by length of the element. If you see here, x2 is 4000, x1 is 0. 4000 minus 0 divided by length of element, which is nothing but 4000. If you simplify, you will get 1. Similarly, y2 minus m is equal to y2 minus y1 divided by length of y1, length of first element. Here if you see, y2 is 0, y1 is 0, so you will get answer as 0. Similarly, we need to calculate direction cosines for the second element. So again, L is equal to, here x3 minus x2. x3 is nothing but, here what we have found out earlier, the nodal connectivity data, in that x3 is 0, x2 is 4000, y3 is 3000, y2 is 0. So 0 minus 4000 divided by 5000 is nothing but length of the element. If you do so, we will get minus 0.8. Similarly, y3 minus y2 divided by length of element, if you do so, we will get 0.6. Once we calculate the direction cosines, next step is to define the elemental connectivity data, where first element, which is connected between node 1 and 2, having its length 4000 mm, and the direction cosines which we have found 1 and 0, L and M. So that's what here you can see, 1 and 0. Similarly, length of second element is 5000. The direction cosines are minus 0.8, 0.6. Those we have found out here. Once you calculate these data, next step is to determine the stiffness for first element, stiffness matrix. Here the stiffness matrix for the truss element is given by A into E divided by L, where A is the cross sectional area, E is Young's modulus, L is the length of the element. And these are the elements which defines the direction cosines. And the matrix, it can be easily remembered, like first we need to remember these diagonal elements. Next we need to determine these, like next it is easy to remember here, L square M square L square M square. Next we need to remember LM minus LM LM minus L square minus M square minus LM. This is how we need to see, this is how we need to remember, since as we know that stiffness matrix is a symmetric matrix, the upper diagonal elements are the same as lower diagonal elements, so I have written only the upper diagonal elements. And here we have written 1 2 3 4, because as we know that the first element which is connected between node 1 and 2, and first node, this first node, yes, this first node has two displacement u1 and u2, and second node has displacement u3 u4. So we have 4 displacements, so we have 4 by 4 matrix, which you can see here, 4 by 4 matrix, 1 2 3 4 1 2 3 4. Next we have, now the thing is, like, we need to substitute these direction cosines for the first element. Direction cosines are nothing but this 1 and 0 for the first element. Those we need to substitute over here. L is nothing but 1, so 1 square is 1, M is 0, L is 1, so it is 0, minus L square means 1 square minus 1, so LM again it is 0. It is very easy to calculate, like once you calculate these element, next the same thing you need to copy over here. the 0 minus 1 0, since it is a symmetric matrix. Next we need to calculate only these three elements. Once we calculate these three elements, the same thing we need to copy over here. Once we calculate these things, next we need to calculate only these two. Once we do that, we need to copy this, and last element we need to determine. Like this we need to calculate. And if you simplify this equation, 600, that is nothing but area, 200 into 10 raised to is nothing but Young's modulus, 4000 is the length of element. If you simplify, you will get 3 into 10 raised to 4, and where 10 raised to 4 is taken as a common and 3 is multiplied in this matrix, and you will get this answer. You will get this answer, 30 minus 30 0 0 0, like this you will get. Once you do that, next step is to determine the stiffness matrix for the second element. Here again it is nothing but K into E divided by L, right? Here cross sectional area is 600, Young's modulus is 200 into 10 raised to 3, length is 5000, and these are nothing but the direction cosines L and M for the second element. Second element direction cosines is minus 0.08 and M is 0.06. Again L square is nothing but, here if you see our matrix, here we have L square. L square is nothing but 0.8 square minus 0.8 square minus 0.8 square, you will get 6.64. Similarly we need to calculate all the elements. Once we calculate that, you will get this matrix. You will get this matrix, means here again if you simplify this, you will get, if you simplify this, you will get 3 into 10 raised to 4. Again we have taken 10 raised to 4 as a common, and we multiplied, like we will get the data, and we have taken 10 raised to 4 as a common. If you simplify this, you will let me know like what the simplification comes. T is 600 into 10 raised to 2, 600 into 600 into 200 into 10 raised to 3 divided by 5000. If you do so, you will get 2.4 into 10 raised to 4, so 10 raised to 4, where we have taken 10 raised to 4 as a common, and 2.4 we multiplied with the elements of this matrix. Once we do that, we get this. Here we have written 3 4 5 6 because the second element which is connected between node 2 and 3, and here node 2 has a displacement u3 u4 and u5 u6, here u5 u6. So we have written 3 4 5 6. Now once we calculate the stiffness matrix for the second element, the third step is to determine the global stiffness matrix. That is nothing but addition of these two matrices. Like since we have 3 nodes, we will get 6 displacement, so the global stiffness matrix is of 6 by 6 matrix. So that's what we have written, 6 by 6 matrix, 1 2 3 4 5 6, 1 2 3 4 5 6. See, once we found the global stiffness matrix, like global stiffness matrix, as we already discussed in the previous video, where and the thing is very simple. Here we need to write first these 6 by 6, like 6 rows and 6 columns. Once we write this, next we need to fill all this data. It is very easy. Like here what we have done, like first row we have taken, first column we have taken, that's what we have 3 over here. Similarly, see, once we do this, like next we need to see like first row second column, here we have 0. How this 0 has came? And a simple thing, again we need to see here, this is our stiffness matrix for the first element, first row, second element is 0. Similarly we need to calculate for all the elements, for 6 element. For example, if you want to calculate the element third row third column, we have 3 plus 1.53. how this has came, we will see now. Third row, this is third row third column, if you see, this is third row third column, third row third column, we have 3 plus 1.53. if you see this matrix here, for the first element stiffness matrix, we have third row third column, we have 3, and here we have again third row, third column, it is 0.64. If you add these two, you will get this answer. Like this, we need to calculate all the elements. Once we do that, the next step is to define these load vectors, means load at the each node. So this is how the our truss look like. It is fixed over there, it is fixed over here, and here we have roller support, means it is moving in the x direction, whereas vertical direction we don't have. Here the application of force is in the negative x direction. Application of force is in negative x direction. So here in this node, F1 is fixed, so F1 is 0, F2 is 0. At in this node we have F5 is 0 and F6 is 0, right? Here in the second node we have F3, we have it is minus 1000 kilonewton, since it is acting in the negative x direction, and F4, that is vertical force, we don't have, that is 0. That's what we have written over here. F1 is 0, F2 is 0, F3 is minus 1000 into 10 raised to 3, F4 is 0, F5 is 0, F6 is 0. Now the global displacement vector, in the sense we have 3 nodes, 6 displacements, so we have written u1, u2, u3, u4, u5, u6. Once you define, next we need to apply the boundary condition here. Before that, we need to write this equilibrium equation, K into Q is equal to F. So K is nothing but stiffness, global stiffness matrix, U is nothing but global load displacement vector, F is global load vector. So once we do this, that's what we have written here. Next we need to apply the boundary condition, that is nothing but elimination